All right, we are going to take a look at U-substitution today. We're going to spend a couple of days on U-substitution, so today we're just going to kind of lay the foundation and kind of look at some patterns and figure out what's going on. So the reason we need U-substitution in integrals is to be able to take the antiderivative of something that we would have used the chain rule for to take the derivative of. So if we had something like d dx of some composite function f of g of x in our first few units, we would have taken the derivative of the outside, kept that inside alone, and then multiplied by the derivative of that inside function. And so now what U-substitution is doing is it's simply undoing that, just like we've seen before. We're now going to be taking the antiderivative of f prime times g of x times g prime of x d of x. And what that's going to give us is that composite function back out, plus some constant. And so U-substitution is all about recognizing a pattern. You're going to be looking for these two pieces. So you're going to be looking for a function that's embedded inside of another function multiplied by the derivative of that embedded function. So you're looking for, again, it's just pattern recognition. So let's go ahead and take a look at some examples. So this is our U-substitution right here. I don't like that. Put a box around it. There we go. Another way to look at that is to let u equal g of x. Then our du, so when we take the derivative of u, would equal g prime of x dx. And so the integral of f of u du is simply f of u plus c, the antiderivative of f plus c. All right, so let's take a look. Let's say we're taking the antiderivative of x squared plus 1 all squared times 2x dx. So again, this is all about pattern recognition. So I'm looking here and I see that I have x squared plus 1, and then the derivative of x squared plus 1 is 2x. So I have that chain rule, right, inside my antiderivative. So we're going to go ahead and we're going to let u equal x squared plus 1, because then du, the derivative of u, is 2x times dx. So notice right here, I have u squared, and right here, I have du. So I'm going to go ahead now and rewrite this as u squared du. The antiderivative of u squared, I add 1, so I get 1/3 u cubed plus c. And then I go ahead and I sub back in my u, so 1/3 multiplied by x squared plus 1 all to the third plus c. Let's go ahead and just prove that this is, and you don't have to do this every time, obviously, but let's just show that this works since this is our first time going through one of these. If I were to take the derivative of 1/3 x squared plus 1 to the third plus c, So the derivative of this, I'm going to use my chain rule. And so I bump the 3 to the top, to the front. So I have 3 over 3 times x squared plus 1. This bumps down to a 2, and then I would multiply that by the derivative of the inside, which is 2x. So I would end up with x squared plus 1 all squared times 2x. And then the c, the derivative of c is just 0, so that goes away. Notice that's the same thing as my integrand that I started out with, so that checks. Because again, these are inverse operations, so they're undoing each other. Let's try another one. I have the antiderivative of 5e to the 5x dx. So my u is that inside function, that g of x. So I'm going ahead and I'm looking for the u. And e is my outer function. That's like my f of x. This 5x is my u. And notice the derivative of 5x is 5. So that's really helpful. So u is going to be 5x. If I take the derivative of u with respect to x, my du is going to be the derivative of 5 times dx. And so I'm going to rewrite this now. This equals the same thing as e to the 5x times 5 dx. This piece right here is my du. This right here is my u. So I have the integral of e to the u du. The antiderivative of e to the u is just e to the u plus c. And then I go ahead and I input back that 5x. So it would be e to the 5x plus c. Again, if I took the derivative of that, I would get 5 times e to the 5x. So it gets me right back to where I started. All right. Let's go ahead and just take a look at, sometimes we have to do a little bit of work to get where we want to be. So let me go to a new page. Oh, I'm good. So let's try this one. We have the integral of x times x squared plus 1 all squared dx. All right, so I clearly see that my inside function is this guy right here, right? So I'm going to go ahead and I'm going to let u equal x squared plus 1. So when I take the derivative of this, so one thing that I just want to clarify, when I'm saying that I get like 2x dx, if I'm taking the derivative of this, I'm doing du dx, that's going to equal 2x, and the reason I'm getting that dx on that side is that I'm multiplying by dx on either side so that I have an expression for du. So just a heads up on that so it doesn't feel like that's coming from nowhere. Okay, so notice that I have a u, so I'm good there, right? This is my u. So I have this u squared, but I don't have a 2. I have an x, so I can rewrite this as x dx, but I don't have a 2 there. So in order to get that 2 in there, I'm going to multiply by basically like a smart 1. I'm going to multiply by both 1/2 and 2 at the same time, because 1/2 times 2 gives me 1. So it's like I'm multiplying by 1. So what I'm going to do is I'm going to slide a 2 right here. So I'm going to multiply by 2x dx, which is what I need. But in order to do that, I need to multiply the outside of this by 1/2. So what we have here is 1/2 times the integral of u squared times 2x dx. This 2x dx is my my du. So I have equals 1/2 the integral of u squared du. So I kind of like made a du by multiplying by 1/2 and 2 at the same time, because I saw that this needed to be 2x. I can do this with coefficients. I can't do this with variables. We're going to have to do something different with variables, but we'll look at that next class. And now I can go ahead and take the antiderivative. So I have 1/2 times 1/3 u to the third plus c. So I get 1/6. My u is x squared plus 1 to the third plus c. And we're all done. All right, let's look at one more example. It's going to follow a similar pattern of what we need to do. So we have the antiderivative of the square root of 2x subtract 1 dx. So again, my u this time is my inside function, so 2x subtract 1. My du is just 2 times dx. And so I have everything I need for this because I have the dx, right? I just needed 2, so I'm going to play that same game. I'm going to rewrite this as 1/2 times the integral of the square root of 2x minus 1 times 2 dx. So again, I multiplied by both 1/2 and 2 so that I can have that coefficient there. This is my du. This piece in here is my u. And then I have that 1/2. And I'm going to rewrite my exponent at this point as 1/2 instead of using the square root. So I take my antiderivative. I add 2 over 2. That gives me 3/2. The reciprocal of 3/2 is 2/3. Plus c. So I get 1/3. My u is 2x minus 1 to the 3/2 plus c. And so we could leave it like that, or we could rewrite this by taking out 1 whole from here, which would be 2x subtract 1. I'd be left with the square root, so square root of 2x subtract 1 plus c.